The content in this video comes from pages 30 through 32 through 36 of your textbook, and it's meant to help you achieve learning objective number 7, which is to compare and contrast latent heat and sensible heat. In a minute, I'll ask you to pause the video and complete a very brief assignment. If you haven't already done so, it's a good idea to skim pages 32 through 36 before you watch the rest of this video and pay particular attention to the bold words, which should include the key terms listed here, and to the figures in their captions. Please plan to read the content more thoroughly before you attempt the online vocabulary quiz or the concept quiz for this chapter. Energy can be thought of simply as the ability to do work, such as making an object move. For example, when your body processes the food you consume, it converts potential energy in the chemical bonds of your food into thermal energy. Your metabolism determines the amount of work required for digesting, absorbing, transporting, and storing the food you consume. And takes that takes a small amount of thermal energy, calories. Your body uses the rest of the energy it generates through thermogenesis to provide mechanical energy that drives your physical activity. A common example of the use of energy can be the heat energy from an espresso machine. It excites the water molecules and extracts the coffee from the grounds. Energy can take many forms and can also change from one form to another. Do you think that the temperature of the liquid in each of these cups is about the same? I do. Let me ask you this, and this might just be a quick pause. Which of those two cups would you rather have spilled on your lap? If I had to pick one, I'd pick the smaller cup because I'd expect it to scald a smaller surface area on my body. In other words, I would expect the smaller cup to contain less energy because it has smaller mass and volume, even though it has the same temperature. So more energy is in the bigger cup. And that's not too hard to remember. And while this seems like we might be getting off the beaten path here, one of the things we have to focus on in weather is the difference between energy and temperature. That can be a tricky concept for new students to master, but in the weather context, look at these cloud pictures. Would you agree with me that the air inside both of these clouds probably has about the same temperature? Well, which one of them do you think contains more energy? The big one, right? Kinetic energy is the energy associated with an object by virtue of its motion. An example of kinetic energy is the motion of a boulder as it rolls over the ground after falling from the valley wall. Because of its motion, we can see evidence that it has moved objects, like the house on the hill, and the upper meter or so of soil in the vineyard. So imagine how much effort you would have to expend to demolish that building with hand tools. And having finished that, go dig a meter deep ditch from the top of this boulder up to the top of that hill. That's a lot of work. So while we don't see the boulder expending kinetic energy in this picture, we do see evidence that it did some work. The higher up on the valley wall that a boulder like this one originates from, the more time it has to spend accelerating under the influence of gravity, and the faster it will be traveling when it comes into contact with something. The larger the force of that impact will be. So the higher the point of origin, the faster the boulder moves, the greater the kinetic energy at impact. In the foreground of the picture here on the left under energy of motion, you can see a boulder there that's about 4 times as large as the one that just rolled into place. Assuming that they both came from the same original elevation, which one do you think had more kinetic energy? In a similar fashion, the winds associated with a hurricane possess much more kinetic energy than do the light localized breezes that we get around ocean shores, because they're both larger in scale, they cover a much bigger area, and they're traveling at much higher velocities. So the other side of this picture shows potential energy. That is energy associated with an object by virtue of its position. So it's the capability, it's the potential to do work. And the picture you're looking at here is Bubble Rock in Acadia National Park in Maine. And this rock has been precariously perched on the precipice here for years. It's not done any damage because it doesn't have any kinetic energy, right? Only potential energy. If the rock were to topple, all of that potential energy would be converted to kinetic energy until it came to rest again. Here are some examples of kinetic and potential energy that pertain more closely to weather. At the atomic level, all matter is composed of atoms and molecules. So we're talking about a very small scale. Those molecules are continually vibrating, and because of that vibration, they have kinetic energy. For example, when a pan of water is heated on a stove, the water molecules begin to vibrate faster. And when a solid, a liquid, or a gas is heated, its atoms or molecules will move faster, and the material then possesses more kinetic energy. I want to point out something unique about water here. Notice that most substances have their molecules combined together most tightly. So they're most dense when they're in their solid state. So if we think about rocks, magma is less dense than the solid rock version. Because of the Mickey Mouse shape of the water, one side of the molecule has a negative charge and one side has a positive charge. And that gives it a bipolar nature. And because of that bipolar nature, ice has a very systematic crystal structure, which you can see in the bottom left diagram with the blue water molecules. The liquid state is actually more dense than the solid state, and that's why ice floats on top of water. So whoever made the top diagram with the red molecules was clearly thinking about water. You know, I can see the little red and white Mickey Mouses in the picture, but they didn't leave enough open space between the molecules. The bottom diagram is correct for water, and the top diagram would be correct if the molecules were of some other substance. At any rate, in its lowest energy state, the solid state, the water molecules vibrate at their lowest speed. So I'm going to say that part again. The lowest energy state for water is in fact the solid state. That doesn't have anything to do with the density, really. It has to do with how much kinetic energy, right? The ice frozen state, all the way over to the left in the blue diagram, shows you molecules that are not vibrating very quickly at all. So they're vibrating at their lowest speed. Water molecules vibrate at their fastest rate in the gaseous state, so steam. They vibrate very quickly, causing many more impacts between one molecule and the other. An example of potential energy from the science of weather is the forces acting on droplets inside a thunderstorm. So inside this big cloud on the right, large raindrops or hailstones remain suspended inside a towering cumulonimbus cloud because the upward force of the warm air inside the cloud is balanced with the combined forces of gravity plus the downward force of the cold downdraft wind. So we have wind pushing up, indicated by the red arrows, and we have wind pushing down, which is indicated by the blue arrows. So if you are in that portion of the cloud between the updraft and the downdraft, and the updrafts are strong enough to outdo the force of gravity, the particles can remain suspended up there. So they are like Bubble Rock in Acadia National Park, the rock that was precariously perched on the precipice. If the updraft subsides or the downdrafts dramatically increase, then the potential energy will be converted to kinetic energy, and raindrops or hailstone will be pulled toward the earth. In everyday use, temperature is used to describe how warm or cold an object is, using some standard measure. In the United States, the Fahrenheit scale is used most often for the expressions of temperature. For example, the Weather Channel may forecast tomorrow's high temperature to be 88 degrees Fahrenheit. We wish in January here. However, scientists in the majority of other countries use the Celsius temperature scale or the Kelvin temperature scale. You can find a discussion of all those temperature scales in chapter 3. But temperature can also be defined as a measure of the average kinetic energy of the atoms or the molecules in the substance. So when this substance is heated, its particles begin to move faster. And because of all of the increased number of collisions between those molecules, the temperature will rise. And by contrast, when that object cools, the atoms and molecules vibrate more slowly and the temperature drops. It's important to note that temperature is not a measure of the total kinetic energy of an object. For example, a cup of boiling water has a much higher temperature than a bathtub of lukewarm water. However, the quantity of water in the cup is small, so it contains less total kinetic energy than the water in the tub. So much more ice would melt in the tub of lukewarm water than in the cup of boiling water. Does that make sense? The temperature of the water in the cup is higher because the atoms and molecules are vibrating faster, but the total amount of kinetic energy is much smaller because there are fewer particles. Heat is something else. It's defined as energy transferred into or out of an object because of temperature differences between that object and its surroundings. So energy transferred into or out of an object because of temperature differences between that object and its surroundings. If you hold a mug of hot coffee, your hand will begin to feel warm or even hot. And by contrast, when you hold an ice cube, heat transfers from your hand to the ice cube, right? It's not the cold that's transferring to your hand, it's the heat that transfers, the energy is transferring from your hand to the ice cube. Heat flows from the region of higher temperature to the region of lower temperature. And once the temperatures become equal, the heat flow stops. It's also common to use the word heat to describe thermal energy. And that is a kind of kinetic energy that's contained in a substance as a result of its temperature. So all this is starting to sound like mishmash, I'm sure. But there's subtle differences that are important as we get into talking more about the atmosphere. So a hot object is described as containing more thermal energy or heat than a cold object of equal mass and composition. That's an important thing, that last bit. A hot object contains more thermal energy, heat, than a cold object of equal mass and composition. So meteorologists further subdivide heat into two different categories, latent heat and sensible heat. As water in the beaker changes state from solid to liquid, latent heat is absorbed from the environment, and the water molecules use the energy to increase their rate of motion. As water in the beaker changes state from gas to liquid, latent heat is given off to the environment, and the molecules adjust to the lower state of energy by reducing their rate of motion. This figure, which is really similar to figure 2.3 in your book, shows the phase change that water can experience. For example, when water vapor condenses to form a liquid, it releases heat to the atmosphere. When liquid water evaporates to form a gas, it also releases heat to the atmosphere. When the rate of vibration is great enough to overcome the strength of the hydrogen bonds holding together the water molecules, some of the molecules escape through evaporation and become gaseous, water in its gaseous state, water vapor. Because the most energetic, the fastest moving molecules escape, the average kinetic energy of the remaining liquid water decreases. And what happens if there's a lower amount of energy? The temperature decreases. So therefore, when you talk about evaporation, we consider that to be a cooling process because heat is being taken away from the environment. So the cooling effect of evaporation is something you experience whenever you get out of the shower or out of the swimming pool. You don't step out of a warm shower into the environment and feel warm, right? You feel cool. That's because energy is being absorbed by the environment and released from your body. Ice can be converted directly to water vapor through the process of sublimation, but this requires a huge amount of energy. So we can skip the liquid state and go right from solid into gas through sublimation. I saw that happen in Utah under very arid conditions in the winter at really high elevations. The extremely low atmospheric pressure associated with that high elevation means that sublimation can occur at a much lower temperature than normal. I also noticed there that water boiled at a much lower temperature for the same basic reason, right? There's less mass of atmosphere above you, and the boiling point and the steam point and the freezing point both drop. As water evaporates, the energy absorbed by the escaping water vapor molecules is called latent heat. And latent means to lie hidden, to hide. So the term latent is used to describe the phenomenon because the thermal energy required to evaporate the water is stored or hidden within the escaping water vapor. So the latent heat stored in water vapor is eventually released, usually to the atmosphere during condensation. When water vapor returns to the liquid state, right? So what else is going on when water vapor returns to the liquid state? Clouds are forming. So that's how we think of clouds forming. Therefore, condensation, which is the opposite of evaporation, returns energy to the environment and is considered a warming process. Through the combined processes of evaporation and condensation, latent heat then transports large amounts of energy from Earth's land-sea surface, mostly to the oceans and to the atmosphere. From the oceans to the atmosphere, I'm sorry. The importance of latent heat is that atmospheric processes are governed by the amount of latent heat being absorbed or released. Keep in mind that latent heat is exchanged between the environment and water molecules anytime water undergoes a phase change. So some of those phase changes involve absorption and storage of latent heat, while the opposite processes release latent heat back to the environment. When water vapor condenses and releases heat to the atmosphere, that's referred to as latent heat of condensation. Figure 2.4 in your textbook shows a developing cloud. And every time a cloud forms, the atmosphere gets warmed. Inside that developing thunderstorm, a vast amount of stored heat energy, latent heat, is given up to the atmosphere as invisible water vapor becomes countless billions of water droplets and ice crystals. In fact, for the duration of this storm alone, more heat energy is released inside this cloud than is unleashed by a small nuclear bomb. And of course, I can't prove that, but that's a mathematical calculation that's meant to make your eyes go wide. Sensible heat is the other kind of heat. And you can see, I think best in this diagram, the lower diagram here, what happens with sensible heat. So you can see a temperature on the y-axis here and energy given off on the x-axis of this diagram. So if we start with frozen water, right, at very low temperatures, I'm right down here at the origin of the graph. Let me highlight. If we start down here, we see we're below 32 degrees Fahrenheit, which is the freezing point of water. And as the temperature rises, we see this line going up at a steep angle. So between the point when the ice starts to melt and the time when we have enough water that's freely floating in its liquid state, we see a pretty dramatic increase in the temperature and in the energy given off. So this level line shows you a constant temperature. So while that ice is melting, the system's temperature remains right there at the freezing point, 32 degrees. Okay, so that's the temperature of the ice water. And once all the ice is gone, we can start measuring a heat change. So once all the ice is gone, we stop seeing a 32-degree combination. And this is the average temperature of the water in the beaker. Certainly the ice is still a little bit colder than the water, but the average beaker temperature will start to rise. And so as the molecules are freely floating through the liquid, we see this increase, boy, look at that wiggly line, an increase in temperature and an increase in the energy given off. That's sensible heat, right? Until the water comes to a boil. And while the water is boiling, if we continue to measure, like we're seeing this thermometer stuck in a pot of boiling water, that temperature should remain at about 212 until all of that water is turned into steam, and then we have steam, some steam warming and some steam cooling off. If we continue to add kinetic energy to the system, if we continue to turn the temperature up, that steam can continue to get hotter and hotter and hotter. But we would be able to measure the temperature change at that point. So no temperature change measurable as long as the water is boiling or as long as the ice is melting. So sensible heat is that heat that we can feel, measure, but it doesn't involve a phase change. It's called sensible heat because it can be sensed. And on a clear summer day, the sunlight absorbed by the atmosphere or your exposed skin causes an increase in temperature. Like latent heat, sensible heat can be transported from one location to another. Warm air that originates over the Gulf of Mexico and flows over the Great Plains in the winter is an example of that. In the United States, TV weather reporters give temperatures in degrees Fahrenheit. In fact, only the United States and Belize, a small country in Central America, continue to use the Fahrenheit scale for everyday applications. But scientists, as well as most people outside the United States, use degrees Celsius. The rest of the world has adopted the Celsius scale. The scientific community universally uses Celsius or Kelvin. Scientists sometimes also use well, let's leave it just at that. Celsius and Kelvin. You won't be tested on any other things about temperature. To make a quantitative measurement of temperature possible, you have to have a reliable scale. Temperature scales are based on the use of reference points. The figure with the two thermometers here compares the Fahrenheit over here on the right, the centigrade or Celsius, it's Celsius now, in the middle, and the Kelvin scale on the left. Notice that you don't talk about degrees. Here's degrees C, degrees Fahrenheit. With a Kelvin temperature, you just say Kelvin. You don't have to say degrees. And just as a goof, I found these pictures of all these different guys. Here's Fahrenheit, here's Celsius, and here is Lord Kelvin. In 1714, Fahrenheit devised his scale, and he used a mercury in glass thermometer. Most of the modern thermometers are alcohol, not mercury. except for the maximum temperature thermometers. We'll get into that later. But mostly an alcohol combination. But he used mercury because the 0 point was the lowest temperature he could attain with a mixture of ice, water, and common salt. For his second fixed point, he chose human body temperature, which he arbitrarily set at 96. So on that scale, he determined that the melting point of ice, the ice point, was 32 degrees. The boiling point of water, the steam point, was 212 degrees. And because Fahrenheit's original reference points were difficult to reproduce accurately, his scale is now defined by using the ice point and the steam point. As thermometers improved, the average human body temperature was later changed to 98.6. That traditional value for normal body temperature was established in 1868. A recent assessment places the value at about 98.2 Fahrenheit. So, we're trying to get that information into my daughter's head, that if you're fever, no, you're pretty healthy if you're at 98.2. That's about normal. Celsius scale in 1742, right? So this is just, a generation later after Fahrenheit invented his scale. A Swedish astronomer named Celsius devised a decimal scale in which the melting point of ice is set at 0 degrees. The boiling point of water is set at 100 degrees. And for many years it was known as the centigrade scale, but it's now known as the Celsius scale, named after the inventor. The boiling point referred to in the Celsius and Fahrenheit scales pertains to pure water at standard sea level pressure. And it's necessary to remember that fact because the boiling point of water gradually decreases with altitude. Because the interval between the melting point of ice and the boiling point of water is 100 degrees on the Celsius scale and 180 on the Fahrenheit scale, a Celsius degree is larger than a Fahrenheit degree by a factor of 180 over 100, so 180 100ths, or 1.8. So that's where this magic number comes from, right? 1.8. So to convert from one system to the other, the allowance must be made for the difference in the size of the degrees. Also, conversions have to be adjusted because the ice point on the Celsius scale is at 0 degrees rather than at 32. And so that's why we see the 32 here and here. Now let me erase that so you guys can see it. So those numbers seem arbitrary, but they actually have reasons to be there. That relation is you can see it sort of graphically in this picture. For scientific purposes, and we're talking mostly about physics kind of astronomy. I don't think that we worry about absolute zero on planet Earth too much. But I could be wrong. I don't know what's going on in all the different realms of technology today. But for some scientific purposes, we need to have a different scale. On the Kelvin scale, it's similar to the Celsius scale because of its divisions are exactly the same. There are 100 degrees separating the melting point of ice and the boiling point of water, but on the Kelvin scale, the ice point is set at 273 K, and the steam point is 373 K. That's because the 0 point represents the temperature at which all molecular motion is presumed to stop. That's the absolute zero number that I was referring to. So no molecular vibration, at least theoretically, at 0K. So unlike with the Celsius and Fahrenheit scales, it's not possible to have a negative value on the scale. And that's one very useful aspect of it, because there's no temperature lower than absolute zero. So Fahrenheit and Celsius are both linked to water, right? We're talking about the temperatures of water. The relationship between them is kind of shown in this little table that I made up, but you can see all these different temperature scales in one diagram on this figure, and I don't remember the number of the figure, but it's pretty easy to find in your textbook. One thing that's interesting to point out here, we have 32 is the freezing point of water, 0 is the freezing point of water on the Celsius scale. A really cold day is minus 30 on the Celsius scale and minus 22 on the Fahrenheit scale. So, I mean, this is cold enough for us, but there's a 32-degree difference. Because the difference between degrees is larger on the Celsius scale, this difference, 30 to 22, is only 8, right? So what's happening? This scale, the centigrade scale, is sort of caught up to the Fahrenheit scale. They cross here, right? And then we see them separate again. So a minus 40 Celsius is the same as a minus 40 Fahrenheit. So anyway, I don't know how many times you'll use that, maybe in pub trivia. Okay, here are some questions to serve as a concept check. Remember, this is 32 to 36. The pagination on the next few, on the last few, I think has been off for the version of your book that we're using this quarter, but they'll get better starting on the next presentation. But use the course content provided on the Canvas site, as well as outside internet sources, to verify that you can formulate answers to these questions. If you can comfortably answer those questions, you're in great shape. If you can't, review the textbook, rewatch the video, and see if your abilities start to improve. If you're still completely stumped, start a discussion on the Canvas site or come get help.